Welcome back to COSC 2325. In this lecture, we're going to look at the shift and rotate applications. So by now, you should be really familiar with all of the shift and rotate instructions and have tried them out. And that's what we did in class. In class, we make sure that everyone tried out all the instructions, at least most of them, and make sure that they understood fully what they were doing. So make sure that you play with those and look at those. I did want to mention two things. Number one thing to always remember is on the shift and rotate instructions, whenever you shift X number of bits out, the control flag will be the very last bit that gets shifted out. So I want to mention that. So the last bit that gets shifted out is the control flag. Whether it's if you shift one, it'll be that one, but if you shift three, it'll be the very last one that gets shifted out. And then the other part that I wanted to mention was on the control flags. There was an example that I was trying to do last time, and I was using the AX register. And when I used the AL register, it worked fine. So if your control flag is not getting set, look at the register that you're using, and that might be the reason why it's not getting set. Okay, so looking at your book here, when a program needs to move bits from one part of an integer to another, assembly language is a great tool for the job. So sometimes we move a subset of a number's bits to position 0 to make it easier to isolate the values of the bits. In this section, there's going to be multiple applications in using some of these rotate and shift instructions. And there's also some practice applications in the review exercises. So let's take a look at this first example. In this first example, I want to remind you of one thing. Let me get a pen here. Here we go. Okay. So whenever we define, let's say, a variable, for example, if we say the variable b, maybe it holds 1, 2, 3, h. Well, let's do one more, 4, hex. Whenever you have an integer like this, so if you remember, the way that we can access it, each byte is going to be, we're going to access it from the very end. So we're going to access the lowest bytes first. So this byte will access first, and then this byte will access second. So when this 1, 2, 3, 4 hex is stored in memory, the 3, 4, this byte is, let's say that it's at FFE0. So I'm just going to write E0 here, the last two numbers of a if I just do an address like FFE0. And then the 12 would be at, depending on if these are bytes, it would be E1, right? So 3, 4 would be first, and then we could access the 12. So whenever we create a pointer, we can point, if we point to the very first byte, so like ESI plus 1, it would give us here. And then if we point to the next one, it would give us this number here, the 12. But when we have an array, when we define an array, and let's say that the array is called A, and the array has the values, let's say it has the values 12 and 34. And let's put one more number in this array. Let's put a 10, okay? So if I have an array, then ESI, my pointer, if I assigned this array A to ESI, so if I did that, then ESI would point to 12. So A points to 12. And then if I want to get to the 34, if these are bytes, if this is a byte array, so if I put byte here, then I would do A plus 1 would get me here, and A plus 2 would get me here. So when I look at an array, we start from the left, and this would be address. Let's say if this is address E0, this would be E1, this would be E2. But we're looking at an integer, it's the other way around. And so when we know that, in this particular example, what they're wanting us to do is to shift multiple double words. So we have these double words. I'm going to show you first how they define it. Let me get my pointer here. So they define the double words. Well, this is different, actually. It's not even. No, actually, this is the same example. So here, they're shifting an array of bytes. Okay, 1 bit to the right. So first of all, let's look at the code. So we're defining an array. It's of type byte. Array size is 3, so it has 3 elements. Each element has 99 hex. 99 hex is 1001, 1001 in binary. So we start with 1001, 1001, like this. Now, what they're doing is they're putting the numbers. So, for example, if we had 1234, they are putting this 34 first in the array and the 12 second. This is really, it's hard for me to explain, but basically if you had, this is hard to see because the numbers are the same, but let's say, here, let me see if I can explain it a little bit better. Let's say that the numbers that they had were like 2, 3, 7, okay? Then as an integer, as a like one number, one hex number. Then what they want to do is take this and put it in this order: 7, 3, 2. So working it from back, from the end forward. And so what they've done is they shift the highest byte at ESI plus 2. So the highest byte is shifted at ESI plus 2. Here's the highest byte. And they shift that to the right. And then they shift this one to the right, and then they shift this one to the right. When they shift this one and this one, they're not going to use the shift command. So this one, they're going to use shift right. But for these two, they're actually going to do rotate. Using so RCR, which is rotate, carry, right, using the carry flag. So the first time we're ECI +2, this is the number. We're going to use SHR, shift right. What shift right does is it shifts this right or the lowest most bit to the control flag, which you see here. And then it adds a 0 to the back. So they added the 0 right here to the back, the empty bit. So now we have ESI +2 that has this number, this binary number. Then ESI +1, let me erase everything here. And we go to ESI +1. So here's ESI +2. We're done with that. Carry flag is 1. ESI +1, we're going to do a rotate, carry, right. Rotate, carry, right is going to first move, rotate out that 1 to the carry flag. No, I'm sorry. We can't do that because the first thing is we've got to move this carry flag to the back. And then once you move that carry flag to the back, then we rotate this very lowest bit to the carry flag. So we move that to that becomes our new carry flag. So our new number is, we added the 1 here in the back, and we shifted out this 1. So our new number is 1 1 0 0 1 1 0 0, the new binary number. And that's for the middle. And then the next one, we're going to do exactly the same thing. Shift carry right. So we see ESI 2, we see ESI 1. The carry flag was a 1. We'll move it to ESI, to the back of ESI, making us have 2 1s. And then we move out the 1 that's here. That becomes our new carry flag. So for this code, so after doing this, we've moved all of the bits 1. We've shifted everything 1 to the right. So because the thing that we wanted to do is shift an array of bytes 1 bit to the right. 1 bit to the right each. And we're looking at bits that are, if you remember, they're going to be, you're going to have, like, let's say you have 1 2 3, right? We want to shift the 1 to the right, the 2 to the right, the 3 to the right. But to be able to do that, because this is not saved as an array, it's just a little Indian order. We're going to have to do, this will be ESI, this will be ESI 1, this will be ESI 2. So that's why they start with 2. Because it's an extended precision integer, and we want to be able to shift each one at a time. Okay. So hopefully it's really hard to explain, but if you'll look at this and then enter this code, hopefully you'll be able to see how it shifts each one. So make sure that you enter the code and try it out. And I think what's better is if you, like right now, this is going to be 1001 for each number. Maybe make each number different so you can see how it actually shifts each value. Okay, so I think I have this up. So we're going to go ahead and try this out. So we're going to say array size equals 3. It's in our data section. And then we'll create an array of bytes. So right now they're doing 99H. We'll start with that one and then try out some other, change it up. So ESI is going to be our pointer. So we're going to say shift right array ESI plus 2. And then comma 1. So we're shifting to the right by 1. And that's going to be the highest byte. So if you think about it, that's going to be the highest byte, which is, right now we're putting into an array, but remember that what we're put into the array, well, I don't have it on here. So go back to here. So if you think about it, that 99 would be like this, 99, 99, and 99, all next to each other. Or if you want to write it out in binary, you would write out 1001, 1001, and you would do that 4 more times in binary. But we can't manipulate this number like this. It's not as easy to manipulate it like this. So we're going to put it into an array. And all these numbers are the same. So you really can't, this is what makes it so hard to think about. But this right here, this very first one, is actually this first 99. But if you look at an array, ESI plus 2 is really at the end. So we'll do an example that has different numbers so that it makes a little more sense. But right now we're just going to code this. Okay, so we shift to the right and then we rotate carry. And then we're doing ESI plus 1, 1, and then rotate carry array ESI plus 1. Okay. So this is going to be the middle byte. Oh, wait. This is going to be the lowest byte. And both of these include the carry flag. All right, so we're going to run this. Oh, so I want to, sorry, I need to put a breakpoint so that we can actually see what's happening. All right. So what you want to do is you want to go down here and look at the memory. If you see at the bottom, I have a tab that says memory 1. If you don't see that, when you're in debug, what you want to do is go to Windows or debug Windows and then click on memory. And it doesn't matter which one you click on. I have memory 1 open. And then here, again, we're going to type the name of the array because that's what we want to see. Array. And if you look at here, you get to see this is element 0, element 1, element 2. There's 99, 99, 99. This first element, this first 99 begins at this address x 000740000. This next 99 is at 4001, 4002, 4003, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This one's at 15, and that's why that's an F right there. That's because that's a byte array. Now, if you make this array a different size, like a word array, remember you right click here and you tell it to show you a different size. Okay, so we can do that at the end when we look at this first. Okay, so right now, let's see if I can move this out of the way. Okay, so right now we're at we're going to step over shift right, and what we're going to shift is ESI plus 2. So that's going to be this this last 99. Okay, so step over, and it shifts by 1. So if I'm going to get a pen. So what I'm going to do is if I write, remember 99 is 99, and 9 is a 1, a 0. This is 8, worth 8. And then this last one is worth 9. So this is another 9, 0, 0, 1. So this one's going to be my carry flag, and I'm going to add a 0 here. So now this is 1, 2, 3, 4. I'm going to divide it in 4 bits. So I have 8, 9, 10, 11, 12. This is 12 because this is worth 8 and this is worth 4. And 8 plus 4 is 12. And 12 is the letter C. Then this is worth 4 here because this is, remember, this is 2 to the power of 0, 2 to the power 1, 2 to the power 2, which is 4. So this is 4. So shifting 1 to the right changes 99 to 4C. And then I'm going to step over. So now I shifted the middle byte to the right. I didn't shift, I rotate carry. So that means that when I rotate carry, the carry flag is going to go to the back. And my number was 1, 0, 0, 1, 1, 0, 0. And the very last one gets rotated. out to the carry flag. So my new number here is C, and this is C. Which is right there. And then I'm going to do it again and step over. And of course, it's going to be CC. So that will shift each one to the right one. So once again, what we're trying to do, let me erase all this. What we're trying to do is we're trying to get some number. So let's say now that we have 99. Well, first of all, let's put this in. So let's say we have the integer that has 99, 98, 96 hex, okay? So when you put it into the array, the first number you'll put is the 96, because 96 is at ESI. So this will be 96. You're working it backwards. 96, 98, 99. So by putting it in the array this way, and then accessing ESI plus 2, we're accessing the very first byte in this hex number. And it will allow us to then shift each byte by 1, but in the array. Okay, so it's kind of confusing, but hopefully you'll play around with it and you'll see how it works. All right, so I'm going to stop that and then go back to here. The next thing we're going to look at is not as confusing. This is multiplication by shifting bits. So we saw before that if we shift to the right, we divide. And if we shift to the left, we multiply by 2. 2 to the power of how many ever shifts we make. So if we look at a binary number, we always say, okay, this least significant bit is worth 1 because it's 2 to the power 0, which is 1. Give me just 1 second. And then, so that's bit 0. Bit 1 is worth 2. Bit 2 is worth 4. Bit 3, oops, is worth 8. So this is 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, and so on and so forth, right? And so if we shift the 2 to the left by 1, then we will have doubled that 2. If we shift the 4, we double the 4. So that's a shift to the left. Let me write the rest of the numbers because this is going to be helpful. 16, 32. So this is 2 to the power of 0. 2 to the power of 1. 2 to the power 2, to the power of 3, 2 to the power of 4. Power 2. Anyway, 3, 4, 2 to the power of 5, so on and so forth. Okay, it's going kind of slow. So if I'm going to multiply, let's say if I say let's multiply 22 times times 2. One thing we also want to remember is that multiplication is the same thing as addition, right? So this is the same thing as saying 22 plus 22. Or I can take this 22 and if I multiply that times 2, I would shift my number once, whatever the number is. So I would say 22. And I would take that number and shift it once. If I shift it one time to the left, let's see what it does. Let's look at this in code. So it makes a little more sense. Let's erase all this. Swear. Sorry, give me a second. Okay. So I'm going to say shift and let's move something to, so let's move to AL 22. And then we're going to shift AL by 1 to the left. So right now we're looking at the registers and stop for a second. Let's go ahead and zero out EAX. Okay. So we see here on the screen, EAX is zeroed out. And then when we step over this instruction, we're going to move 22 to AL. And this 22 is the decimal 22, not the hex 22. So that's why you see 16 here. And then the next thing is we're going to shift that 1 to the left. So we step over it and 16, it's kind of hard to see because of 22. Let's choose something easier, like a 10. So 10, we have to convert. 10 is A in hex, so we see A in hex. And then when we double the A, it's going to be 20. So to get 20 in hex, you're shifting 1 to the left. So first of all, if you'll write out 20 in hex, make it even easier. There we go. Okay, so let's step over it. We have 5. Shift to the left, we get a 10. So if you want to go and convert the hex to, so in this previous one, if we have a 10, and then you convert that 10 to, so we have A, so if you convert 14 from hex to decimal, you'll see that it's a 20. Okay, so that's shifting to the left. And that's by 1. So that multiplies by 1. So if I want to multiply my number, and that multiplies by 2. So if I want to multiply, where was I? If I want to multiply by, let's say 4, so if I want to, let's see if I have, let me get an example here, sorry. So if I want to say, let's look at this example here. It's a big one. Okay, so if I want to multiply by 4, then I would move over. If I shift 1, I multiply by 2. If I shift 2 to the left, I'm going to multiply by 4. If I shift 3 to the left, it's going to triple my number, right? So let's look at that in here. So let's do by 3, and then this time, let's put 3. So I'm going to run it. So I have zeros, 3, and I'm going to shift left 3. So my 3 is 3 times 3 is 9. 9 times 3 is 18. So it's actually 3 to the power of 3. So 3 times 3 is 9. And then, no, I didn't do that right. 3 times 3 is 6. And then 6 times 3 is 18. So if I want to to here. So if I want to do something bigger, like this example, where they're multiplying, they're going to multiply 123 times 36. So we want to multiply 123 times 36. You have to find the factors of 36. So what they've done is they said, okay, well, I can do 32 plus 4 is 36. And remember, I had drawn this up here and I took it out, but I had the 1, 2, 4, 6, 8, 16, 32. So 32 and then 4 would then equal 36. So those are the 36 is our multiplier. And so what we're going to do is we're going to shift left 5 and shift left 2, because 2 is 2 to the 4, 2 squared, which is 4, and 2 to the 5th is 2 times 2 is 4, 4 times 2 is 8, 8 times 2, sorry, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. So 2 to the 5th is 32. So we're going to shift left by 5 and shift left by 2. And what we're doing here is first we move 123 to a register. Then we move EAX to EBX. And we shift EAX, which contains 123, we shift it left by 5. And then we shift EBX, which is also 123, we shift it by 2, and then we add those together. So once you do the 2 shifts, then you add it together. So let's say that we want to multiply 123 by, first of all, we'll do even numbers. We'll do odd, is going to be a little bit different. So we're going to multiply 123 times, let's say, 40. So we know that we have 32. So if we multiply 123 times 32 plus 123 times 8. So let's move 123 to EAX. Let's move 123 to EBX. And then now, delete that. We're going to shift left both EAX and shift left EBX. EAX is going to get shifted over by 2 to the power of 5, which is 32. And so we're going to put a 5 there. Okay, so if you shift it over by 5, you're shifting over by 2 to the power of 5, which is 32. And then we're going to shift EBX to get 8 is 2 times 2 is 4, 4 times 2 is 8, so 2 to the power of 3. So we're going to put a 3 right there. And then now we're going to add EAX and EBX, because EAX is going to have 123 times 32. It's going to be the value there. So we have add EAX and EBX. So I'm going to get my calculator. What I'm going to do is I'm going to multiply 123 times 40, and that equals 4,920. But I know that that's going to be saved in hexadecimal. So I'm going to find out what 4920 in hex is. $49.20 in hex. I'm just using a hex to decimal calculator. Wait, no. I need to do it the other way. I need to do, this is a decimal. So my decimal is 4920. And then my hex value is going to be 1338. So I multiplied 123 times 40, and that gave me 4920. And then in hex, it's equal to 1338. Okay, so it's gonna move 123 to EAX, and 123 in hex is 7B, and then it moves 7B to EBX. So now both of these registers have 7B. We want to do the shifts in two separate registers and then add it together. So we're going to shift left the first register EAX by 5, and then shift the next one by 3. And then we're going to add them together. So we'll add EAX and EBX, and the value is going to be stored in EAX. And the value in EAX is 1338, which is the hex number for 4,920. Okay. Now, let's say that instead of multiplying by 40, we want to multiply by 41. Okay, so I'm going to pull out my calculator again, and I'm just adding 123 to it, but 123, and listen to what I just said, 123 times 41. So the answer to this is 5,043. And what just came out of my mouth is I'm just adding 123 to this total. So because it's 41, you can't, there's not, this is 2 to the power, right? So there's not going to be anything that comes out that you add together that comes out to 41. So what you have to do is you have to do the 32 plus the 8, just like we did here, everything that we did here. And then at the end, you just have to add 123. So if it's an odd number, after you do all this, you just say add to EAX 123. And there's no other way to do it. You know, it's just the way it is. So the value for 5,043 in hex is 5,000. 13B3. So let's run this. EAX, EBX, shift EAX, shift EBX, add EAX and EBX, put it into EAX. And then, which is what we had earlier, we're going to add 123, which gives us 13B3, which is hex of 5,043. Okay, so test this out, play with it. You're actually going to have a lab assignment where you have to do this. So this is going to help you out with that lab assignment. Great. What's next? Displaying binary bits. Okay, this little program here, what they're doing is they're taking a binary number and they're converting each bit into a character. So they're making a string. So if you have like 1001, 1001 as a binary number, they just want to convert it to a string. They don't want to convert the number to a string. They just want to see a 1 as a character, a 0 as a character, 0 as a character, 1 as a character, 1 as a character, 0, 0, 1. So just a string. When I first read this, that wasn't super clear to me, but then once I looked at the code, then I figured out that's what they're doing here. So what we see here is they're taking, see how they're putting the 0 in a single quote, So they're saying if there's a 0 in the first byte, then put a 0. If there's a 0 in the, otherwise put a 1. If there's a 0 in the next byte, put a 0, a character 0. If not, put a character 1. So they're building a string from this binary number. That's what they're doing. So they push ECX. Remember, ECX is used as your counter for your loops. They're pushing that value to the stack. They're pushing ESI to the stack. And then they're moving 32 to ECX. They move 32 to ECX because they're converting a 32-bit binary integer. They're going to get the binary integer. It's received in EAX. And they're going to, an ESI is going to point to the buffer. It returns a buffer filled with ASCII numbers, with the ASCII binary digit that it receives. Okay, so we enter our loop and we're going to shift left EAX. So it's shifting the high bit into the carry flag. And it does that because it wants to check. And so it's gonna first assume that that high bit that it just moved is a 0. It doesn't really know it's a 0. It's just gonna assume it's 0. It's gonna move a 0 to ESI, which is gonna be the very first character in our string. And then it's gonna jump if there's no carry. So if we moved, if the highest bit, because we're moving left, the highest bit was a 1, then it's gonna jump here. It's gonna, sorry, if it's not a 1, jump if not carry. But if it is a carry, it's gonna move this to our string. So let me show you. We have, let's do an example. Let's say we have 1, 0, and we'll make this short so we don't have to do all 32. If we go 30 through 32 bits, we're just going to go through 4 bits. So, oh, excuse me, this is EAX. EAX. And we're going to shift to the left. We're going to shift this one to the left. So it actually has a 1. But it's going to go ahead and just put a 0 into our buffer. So this is character. This is going to be a string of characters. A string of characters, 1s and 0s. Okay. I'm going to put it like this. So it puts a 0 in there. And it says jump if no carry. Well, there is a carry, so we're not going to jump, right? Because carry is set to 1 right here. And we're going to move 1 to ESI. So we're just going to override what we just did. This 1 is going to go away. And it's going to put a 1 there. And then after it does that, it goes to this instruction. It's going to increase ESI. So now ESI is here. And then it's going to loop to L1. It's going to shift this number again, EAX, and now we have a 0. It's going to put a 0 into ESI, where ESI is pointing to. And it's going to say, okay, jump if no carry. Well, there is no carry because now our carry flag is a 0. So it's not going to, so it's going to jump to L2. So it's going to skip this line and jump here to L2, and it's going to increase ESI. So when we increase ESI, now we're here. And now we're going to get, now we're going to do shift left And now our carry flag has a 1. And yeah, so we shift left, carry flag has a 1. We're going to go ahead and write a 0 anyway. But then we're going to say jump if no carry. Well, there is a carry, so now we're going to move a 1 into the spot where we had a 0. And so on and so forth. Okay? At the end, when it does all 32 of these, you're going to have this buffer that contains your string of the binary the string representation of the binary number. And then you pop ESI. When you pop ESI, what you're popping is this. This is ESI right here. And then and actually it points to this first one. ESI points to the first part of the array. And then it pops ECX, and ECX was whatever ECX was when you first came into this procedure. It does not say what it is. So, but we messed with it. We assigned 32 to it. So we went ahead and put it back. Okay, and that's the end of the procedure. So this is how we iterate through a binary number and convert it to a string. So again, I suggest that you look at this, type it, run it. I typed it and ran it and was able to see how I just converted it to characters, character 0, 1, etc. Okay, the next example that it shows you is how to extract file date fields. So this binary number that you see here represents a date. Bytes 0, or not bytes, but bits 0 through 4 represent the day, bits 5 through 8 represent the month, and bits 9 through 15 represent the year. Now, this is relative to being 1980, okay? So they're assuming it's 1980. What they're going to do is they're going to add to 1980 a 1 or a 2 or a 3 or an 18. So it's relative to 1980. So let me grab a pencil again. All right, so this day right here, if you start here at 0, remember this is worth 2, 4, 8. So the day is 10. And then the month, this is starting here, this is worth 1, this is worth 2. So the month is 3, March. So it's March the 10th. And then this is worth 1, this is worth 2, 4, 8, 16. So 16 plus 2 is 18 plus 1 is 19. So the year is 1980 plus 19. So 1980 plus 19 is 1999. The day is 10. The month is March. So they're going to show you how they extract this. So let's erase this and move down a little bit to look at the code. And I want to look at the code with the bits here and move a tiny bit. So this is DL. So this is the lowest byte and this is the highest byte. So remember that bytes to make 1 byte, you need 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. So here we have 8 bits, which makes 1 byte. And then here we have 8 bits, which makes 1 byte. Hold on 1 second, my battery's dying. Okay, so not sure what it's doing. There we go. Okay, so the first thing that it does is it moves DL. It moves DL into AL, so it makes a copy of the eight, the first 8 bits. And then it does an and. So AL is ANDed with this byte. And what this byte does is it clears bits 5 through 8. So let's look at bits 5 through 8. This is bit 0, 1, 2, 3, 4, 5. Thank you. Let me plug in before my computer dies. Okay. All right, so to clear bits, remember with the and, a 1 and a 1 keeps the 1, right? So 1 and 1 is 1. So it doesn't clear that 1. But if you have a 0 and a 1 is just 0. So to clear something, we look at here, to clear it, we're going to clear 5, go back to here. So 0, 1, 2, 0, 1, 2, 3, 4, 5. So we're clearing 5, 6, 7. So the reason we're clearing those is because the day is 0, 1, 2, 3, 4. The first 5 bits is the day. So we don't care about the rest of them. We want to clear them out. So to clear them, we're going to set those 3, we're going to AND with 0. So this will be AND 0 and 0 and 0. And so that will clear them out. That will make them all zeros. Here we AND these with 1s. So a 0 and a 1 is 0, keeps that a 0. A 1 and a 1 is a 1, keeps that a 1, etc. All right, so once we clear those out and it clears these with zeros, these 3 with zeros, then we're going to move AL to day. So we can move this to a variable called day, because now we have the day. So we've isolated the day, we made all these zeros, and we saved DL into AL. So now it's okay, the month hasn't gone away. What we want to do is, let's move down here. We're going to move DX into AX. Remember, DX is, oops, so DX is going to be this whole thing. So DX is DH plus DL. So this whole thing is DX. So we're going to make a copy of DX. And after we make a copy of DX into AX, we're going to shift right 5. Shift right 5. So when you shift right 5, go back here. 1, 2, 3, 4, 5. You move out the day. So now all these bits that whole day are moved out. So when you shift right, since you shifted those over, what you're going to have is 1, 2, 3 with 5 zeros. So you'll have 5 zeros in front here. The all zeros, 5 of them, and then 1, 1, which leaves you the month. So if we look down here, we end AL with zeros and 1, so that clears bits 4 through 7. And then we move AL to month. So we shifted these down, and when you shift down, you have to clear bit 1, 2, 3, 4. So 4 through 7. And actually, when we shifted, we didn't add zeros to the back. It actually just shifted these into, so it became 1, 2, 3, 4, 5, 6, 7, 8. So it just cleared these out right here. And that gives us the month. And the last thing that we do is we get the year. And to get the year, we make a copy of DH. So DH actually has the year right here, right? We just need to shift down 1 so that the year starts here in DH. So they're going to shift right 1. Then they're going to move 0 to AH, which clears AH to zeros. So let's go back up here. And then they're going to add 1980 to AX. And then they're going to move AX to year. So shift right, move zeros to AH, and add 1980 to AX. Okay, let's take a look at these review questions. So this first one says, suppose you wish to write assembly language instructions that multiply EAX by 24 using binary multiplication. Which of the following code sequence would accomplish this task? So go ahead and pause the video and figure out which one of these is correct. So here's how I'm going to look at it. So first of all, it's asking me EAX by 24. So I'm going to so I need to find out what adds up, what two, if I factor these out, will add up to 24. So 2 to the what plus 2 to the what. So I know 16. So 16 is 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, so 2 to the 4th power. And then, so that's 16, and then I have to add 8, so that's 2 to the 3rd power. So if I take EX multiply times 16, and then, which is 2 to the 4th power, and then EAX times 8, and add it up, which is 2 to the 3rd power, then I'll get my answer. So I'm going to have to shift to the left by 4 and shift to the left by 3. So let's find that one. So they copied EAX to EBX. They shifted by 4 and by 1. Here's a 4 and 3. There's 2 that have 4 and 3. So let's take a look at these. This one, they copy EX to EBX, shift EX by 4. Oh, they're shifting right here. So we don't want to shift right because if we shift right, we're dividing. So we want it, so this is the right answer. shift left by 4, shift left by 3, and then add the 2 together. And it says correct, so we're good. Let's look at the next. The next one says, suppose that you wish to assembly language. It doesn't sound right. Okay, so we're missing 2 assembly language instructions. Okay, we want to use assembly language instructions that multiply EAX by 21 using binary multiplication. If we express the value EAX times 16 plus EAX times 4 plus EAX, the following code is missing 2 lines. Okay, so we have to add the lines that are missing here. So we moved EAX to EBX, EAX to ECX. We shifted left 4, so that took care of this. So we need to shift left. Oh no, sorry. So 2 times the power, 2 times 2 is 4, 4, 4 times 2 is 8, 8 times 2 is 16. So this is 2 to the power of 4. So this left shift took care of this instruction. And now we need to do this one. So it'd be 2 to the power of 2. So we're going to shift left 2. So here's shift left 2 right there. And then we're going to add EAX and EBX. So EAX, we'll add EBX, and then we're going to add ECX back to EAX. Yeah, so that's the correct one. Make sure you do these before you see me do them. Make sure you try to do these by yourself. Because I know that I'm probably going way too fast. Okay. Let's look at the next question. What change would you make to the bin to ASCII procedure to section 7.2.3 in order to display the binary bits in reverse order? In order, oh, okay. So let's go back to that. So we wanna display the binary bits in reverse order. So if we have the number 1011, we want the string to be 1101. Okay. So if we want to go and bind in a reverse order, here's the program. Then so here we shift. We look at that bit, right? Whether it's a 1 or a 0, whatever. Here we're putting into buffer ESI. So instead of putting in ESI, let's see, it says change the instruction at label 1 to ROREX1 or 2 to add ESI, comma 2 to ESI. Oh, I think I read this wrong. What change would you make to bin to ASCII procedure instruction in order to display the binary bits in the first order? Okay, so instead of shifting, we were shifting, what we were shifting. So here we're shifting left, so we just need to shift right. That's what we need to do to go in backwards order. So I would say this one, change the instruction label L1 to shift right. Yep. So then he gets the last one. Okay. And the last one says, suppose the timestamp field of a file directory entry uses bits 0 through 4 for the seconds, Okay, let me write this down. So 0, 1, 2, 3, 4. So those are my seconds. I'll put S for seconds. And then 5 through 10 are minutes. So how about I do this 5 through 10 for that faster. Oops. Minutes. The 11 through 15 are hours. H for hours. Assume dx already contains timestamp data. Which of the following instruction sequence correctly extracts the minutes? So we want to extract this here, the minutes, and copies the value to a byte variable called b minutes. Okay. So first of all, I'm looking at the answers. Bit 5 through 10 would be 5. So first of all, I got to do a shift to the right. And I need to shift these this way. I want to shift these out. So I'm going to shift out 1, 2, 3, 4, 5. So I'm going to shift 5 to the right so that because I don't need the seconds. So I'm going to shift right by 5. So it's either this one or this one. And then once I do that, I have, so I have 5, 6, 7, 8, 9, 10. That's 6 bits, right? So there's 6 bits here. I want to keep those 6 bits. So those 6 bits I have to AND with a 1. There's going to be 6 ones. And then the 2 bits from here, from the hour, I'm going to AND with a 0. So I have to have 2 zeros and 6 ones. And that would be this one. So that would be my answer. Okay. So that's the end of just a small review. Make sure that you enter this code if you haven't. Make sure that you really play around with it and know exactly what's going on. Only way you're going to do well on the exam. For the exam, for the final exam, you're actually going to be writing code. And there's also going to be a project that you're going to be doing that where you'll have to write some code. So make sure you get some practice in, okay? For the next class, to prepare for the next class, make sure that you look at section 7.3, multiplication and division instructions. So these are going to be just some instructions that allow us to do multiplication and division. So look at all these. And that way, when I do the video, hopefully it'll be a little bit familiar. Okay. With this chapter, we're actually going to cover section 7.3, 7.4, and 7.5 will be the last section that we cover. Maybe 7.6. Hopefully we'll have time to cover everything. Okay. All right. Happy programming. Thank you.